Today we're going to take a look at stepper and servo motors in more detail. And we're going to be able to use TinkerCAD simulation to take a look at the servo motors, but unfortunately not the steppers. So we'll take a look at a few other resources that can help you understand their operation a bit better. So just to go over it again, servo motors is actually a little bit of a tricky term because a servo can actually refer to any motor so long as you can monitor its position and have a feedback loop so that you can tell it go to this position and stay there. And when an external force acts upon it, the position monitor will detect that it's starting to move and it'll change the power going to the motor to hold that servo in position. So you don't have to buy a servo motor per se. You can make your own servo motor using a standard DC motor, some gear reduction, some form of position sensing, either digital or even just a potentiometer, and your own code and your own motor controller, and that is a servo motor as well. Servo refers to the fact that it goes to position and stays there and has feedback and a control loop involved. Now, typically, when we talk about servos, though, we're talking about small little motors in rectangular cases that we use in all sorts of hobby and radio control electronics projects. And the motors are not continuous rotation. So in other words, unlike a DC motor or a brushless motor, it won't which will continue to spin around and around and around and will be great for like drive systems or wheels or something like that. A servo motor will be limited in its range of motion because its goal is to point in a certain direction and to stay pointing in that certain direction. And instead of you telling it how fast you want it to go, you tell it where to go to and you let it worry about what it needs to do to stay in that position. So here's two typical sizes. This is an SG90 right here and a larger, more powerful one. We'll take a look at them inside in just a moment. One of the things that you can do with these though is that you can go in and you can take them apart and you can hack them and you can turn them into continuous rotation motors, and they do make a good source of inexpensive gear motors because you also have your motor control board inside there. So it's one way that you can hack this around and get yourself a nice little gear motor to drive a robot or a little vehicle around with. So here's a backlit SG90 servo. This cost, I don't know, $3 or $4. And just some of the terms that you'll see us use when we're talking about your standard hobby servo motors. I've taken the little control horn off of there. That was what was mounted on the output shaft before. So here you can see the output shaft and how it's tied in to a gear right in here. Now the motor comes right up in here and it's just a standard brushed DC motor controlled by this control board right here. There's a potentiometer tucked in here that is tied into your output shaft. So as the output shaft turns in position, it controls the position of the slider, the center part of the potentiometer, and that sends an analog signal down to the control board that lets it know what direction the potentiometer is pointing. That tells it what direction the output shaft is pointing, which tells it which direction the control horn is pointing. It then takes that and takes power from outside, modulates the power to control the brush DC motor to spin its motor to get the servo to point in the right direction and to hold it in that position if somebody tries to apply a load to it or pushes on it. You'll notice it's a multi-stage gear reduction, so a little gear drives a big gear, which another little gear drives another big gear, and another little gear drives another big gear, drives a medium-sized gear, which drives a bigger gear. And you can see as we get towards the outside where the torque is starting to multiply, the teeth start getting larger because each step down here, the gears will be spinning slower, but they'll be turning with more torque or more force. So it would be very easy to stall the motor right here, but out here it pushes quite a bit harder. So that gear reduction is really critical to how a servo motor is going to work. So this is looking inside a slightly better quality servo. This one probably cost you in the range of $10 to $20. maybe a bit more with the metal gears in there. Sometimes you'll get a mix of metal and plastic gears, and they'll only use the metal gears in the very final output stages where the torque is the highest. And you can keep going on and you can get larger motors. You can get brushless servos. So if you want something more efficient and more expensive, you can get a brushless motor in here instead of a brushed DC motor. You can get a digital encoder in here instead of an analog potentiometer. So they're going to have longer life and a little more precision. But this is a fairly nice servo motor right here. And what you see is that definitely the metal gears, huge change in the amount of strength that you're going to be able to transfer out to your output shaft. In here you can see the potentiometer that is tied into the output shaft right here. The output shaft fits into that slot right there that turns the head that you mount the control horn on. So this one's actually broken down into 3 pieces. This part pops onto the top right here, and then this part right here drops down onto the bottom, and they all bolt together in 3 separate pieces. And you'll see that the servo motors that we use will typically have 3 wires coming into them. And that's because our servos use something called servo pulse width modulation. Now, we've used the term pulse width modulation to describe how we would dim an LED or slow down a motor. And in that case, what we're doing is we're primarily talking about the duty cycle of the pulse width modulation, the fraction of the time that it spends on relative to the fraction of the time that it spends off. But in servo PWM or hobby PWM, it's using the pulse width, the amount of time that it's on for, to transfer a different bit of information. The length of that pulse, instead of actually being a power signal, is a control or logic signal, and it's telling the arm which direction to go to. So this is a snapshot from the SG90 manual, and it tells us that, somewhere on these motors, somewhere between a 500 to 1,000 microsecond, so 1,000 microseconds being 1 millisecond or 1/1000th of a second. So this is somewhere between 500 and 1,000 millionths of a second on that pulse right there. You turn it on and turn it right off right away afterwards, and that will put your arm at the negative 90-degree angle. Come up to 1,500 microseconds, and it'll swing over to center or neutral, and 20 to 2,500 seconds. So this is on for a longer period of time, and it will swing over to this side, which we're calling minus 90. So you have to send a signal every 20 milliseconds. Otherwise, the servo is going to say, oh, they've forgotten about me, and it's going to stop holding position because it's going to assume that there's been some form of data loss, signal loss, that your microcontroller shut down or something like that. So 20 milliseconds, that's 50 times every second. You need to send this little pulse just saying, hey, I'm still here. This is the position I want you to go to. Now, you can do that a couple of different ways, and you can simulate a servo in TinkerCAD very well. They have a couple of different styles of servo in there. Very easy to wire up on there. And you can manually tell the Arduino to send out a series of pulses of different widths. So right here, we're going to start with a 500 millisecond pulse, and we're going to go up to 500 microsecond pulse. We're going to go up to a 2,500 microsecond pulse, and we're going to increment 10 microseconds each time we do that. I'm still impressed that we're talking about microseconds as if it's not a big deal. That's millionths of a second. And the Arduino is just like, yeah, whatever, millionth of a second. Tell me what to do, boss. So what we're going to do is we are going to do a digital write. And so this is all happening within a loop where the delay pulse width is going to be changing right in here because it's part of a for loop, and each time this loop iterates, the pulse width increments by 10. So we're going to start at 500, and we're going to send a 500, we're going to set the pin high, wait 500 microseconds, set it low, and then this is a 15 millisecond delay, so 15,000 microseconds, so that we get that signal out at least once every 20 microseconds. And then you can actually watch that signal change as you go up. And so this is just going to keep repeating. Next time we come back, it'll be 510 microseconds, so it'll move a little bit over, and it'll keep going until we get up to 2500 microseconds. Now, go into TinkerCAD and hook up a servo like this. Takes you a fraction of a second, and try punching in some code just like this. And what you'll see is that the servo will move nice and smoothly over to one side, and then when it hits the 2500, it'll swing back to this side, but it'll never actually get all the way back to the position that it should be in at 500 using this code. So go ahead and simulate it and see if you can figure out why it's not getting back to that position, and maybe come up with a way of making it get back to the 500 microsecond position. Now, that's manually coding it, where you manually control the pulse length that's going out there. Servos are used often enough, and quite frankly, we often want to use more than one servo on a system, and if you had to manually write the code all the time, it would start to become a bit of a pain in the butt, unless you knew more about timers and interrupts, and at this level, of course, we haven't gone that far. Thankfully, people who do know about timers and interrupts have written a servo library for the Arduino and have included examples in the Arduino IDE. So you can go and find code for using servos, and you can either use the knob command to control the position of the servo with a potentiometer, or the sweep command, which will gradually move the control arm back and forth. So that's in the IDE for Arduino. It's one of the libraries that's included. And just a couple things that you should know when you're designing a circuit using this is that because the servo library runs using one of the timers, which are little hardware circuits built right into the Atmega chip on your Arduino. So something built right into the brain of the Arduino. They have these timers that keep track of things for you. And because we're using one of the timers, that means that to control our servos, that means the timer is not available for other things. And the other things that the timer that we're going to use in the servo library used to take care of was it used to take care of generating the PWM signals on pins 9 and 10. So if you're trying to dim an LED or slow down a DC motor or anything like that using pins 9 and 10 on the Arduino Uno, then what you're going to find is that your servo library interrupts with that. So if you're designing a circuit, it's probably a good idea to hook up your servos to pins 9 and 10 for their control, because then you don't lose that pulse width functionality. You were going to lose it anyway because you had servos plugged into those pins. The library also assumes that you're going to be working with servos that have a range of 544 to 2400 microseconds. And when you define your servo by doing the servo.attach instruction, you'll see that in all the example code. When they do servo.attach, they'll do the simplified version of it, and they'll just say which pin to attach it to. But you can actually add two other parameters into it, minimum microseconds and maximum microseconds. So if your servo worked really well between 1000 microseconds and 2200 microseconds, then you just say servo, you tell it which pin your servo.attach, you'd tell it which pin you're connecting to, and then you'd say 1000 and 2200, and then it would know how to map that out and give you the correct position for your servo. Now, with servos, they tend to be a little bit forgiving on that. If you go past one end or the other, that's not that big of a deal. But the servo library and the servo language and this concept of servo PWM is also used in a number of small motor speed controllers. So particularly anything that might transfer to or from the radio control industry. This servo protocol has been around in the radio control industry for making radio control airplanes and cars for decades. Back before the advent of microcontrollers and all that and fancy pants digital communication system, this was a way of communicating the desired position of steering or airfoil control surface positions to airplanes and any number of radio control devices. The rudder on your radio control sailboat you'd you'd be able to control it by sending a pulse width signal. But a speed controller on your radio controlled car just took that same thing, and now if you send a 500 microsecond signal to your radio control speed controller, it'll assume that means full backwards. And if you send it a 1500 microsecond signal, that'll assume stop. And if you send it a 2500 microsecond signal, that will be full forward. So a lot of radio control speed controllers use this exact same protocol. So if you can control a servo, then you can probably control an entire radio control vehicle using just your Arduino. And you can actually do some neat things with it. I had a student last year. He took a radio controlled truck that he used to play with when he was a kid, and he popped an Arduino into it and put the Arduino between the radio control receiver and the steering and the motor controller. And then he attached a rangefinder to the Arduino. So he actually was able to install automatic emergency braking and add a device to his radio control car so that even if he tried to slam it into a wall, the rangefinder would detect the wall approaching. The Arduino would then be able to block the signal from being transmitted from the radio control device to the motor, and the motors would come to a stop and the vehicle would actively brake to avoid the wall. So you can do some neat things like that when you understand how the servos work. Now, stepper motors are another kettle of fish. I've got servos and steppers in the same slide, but mostly the thing that they have in common is that they're both electromechanical devices with an S at the beginning of their name. They function quite a bit differently. There's no gear reduction necessarily built into most stepper motors. They are continuous rotation, and they have no feedback loops inherently built into them. Usually you have to add some type of feedback loop to your stepper motor, but they are capable of giving you very precise motion control and are used extensively in 3D printers and CNC machines. So the trick behind the stepper motors is that let me just bring up a window here. There we go. Lovely little animation on YouTube, and you can go on YouTube and you can see these great animations indicating how your steppers are going to work, and they'll talk about this in piece by piece, how you've got multiple coils in here, and as you change your electrical signals to the coils right in here, their magnetic fields will change both strength and polarity, so that right now the rotor, which is this variable reluctance shaft right here, is being held between those two coils. But when you use the semiconductors attached to your device to energize the next coil over, it pulls that rotor over towards that. And then when you energize the next coil, it comes over right to here. And you can control these coils, both which coils are on and which end is north and which end is south. So you're able to start pulling that around. There's also some very interesting labs online. So one that came up for me was from, it looks like New York University, NYU, and they actually have a really nice lab that walks you through about how to use your L293D H-bridge to control a stepper motor. And it's got some nice diagrams that explain how it works. And although that really looks like a TinkerCAD model right in there, it's got to be from Fritzing or something else, because I have not been able to find a stepper model in TinkerCAD as of March 2020, which is too bad because it would be really awesome if they had it. So let's just bring that down and come back over here. So again, you'll find lots of information. If you just go to YouTube and take a look for videos of stepper animations, it really wasn't worth my while to recreate one of them here. So let's see, stepper motors. They are a type of brushless motor. Now what that means is that in a standard DC motor, you've got brushes that are conveying the electricity to the rotor, the spinning part of the motor. And in our stepper motors, because the coil is fixed, the coil is now the stator, and the magnets become the rotor, that we never have to go through a brush. Our wiring stays fixed all the time. What we have to do is we have to take semiconductors, an H bridge essentially, and we have to control how that H bridge directs the current through our coils. There's different types of rotor that you can get, and I made mention to the variable reluctance in that little video clip that we just took a look at. You can also get permanent magnets fixed onto the rotor, and there's also the hybrid synchronous technology where steppers can use a mix of permanent magnets and soft iron cores. Your semiconductors control the direction of flow. Whoops, sorry about that. And critical to note is that there's no feedback built into these, so that when you go to hook them up, you usually have to, first of all, make sure that you choose a powerful enough stepper motor that it's going to pull your device through whatever normal drag you're going to expect. You need to have enough torque on there that when you tell that stepper motor to move one step to the left, it always moves one step to the left, regardless of what the load is on it. Because if it doesn't make that move, you don't necessarily have a feedback mechanism to tell you that, ooh, missed that step. So you can quickly lose position of where your motor's at if it doesn't have enough torque, and you're sometimes missing steps on it. The other thing is that you don't know where your stepper motor is starting out. So you'll notice that anytime you're using a CNC machine or a 3D printer, that the first thing you have to do is set your home position. And on the 3D printers, that's typically done using limit switches. There's a routine that starts up, and your 3D printer, before you start printing, will move, and there'll be a switch in the X, Y, and Z axis that has to be pressed. When that switch is pressed, that says, okay, I'm at home, I'm at 0 on this position, and now I can start counting where the stepper moves me to. So you do have to have some sort of feedback device to know where you're at with a stepper motor. Okay, there's a couple of different ways of winding steppers. The ones that we'll see most commonly will be the bipolar motors, very common for do-it-yourself stuff. And sometimes you'll see 5, 6, 8 wires. And some of those different models, for instance, our NEMA 17. NEMA 17 actually refers to the size of the motor rather than any electrical characteristics of the motor. But our NEMA 17 motor right here, you can see actually has 6 wires coming off of it, but you can run it quite happily with 4. Just look up the wiring diagram for a NEMA 17 if you're using that type of motor. If you're using some other types of motor, you may have to go online and do a little bit of research to find the correct wiring diagram and which color wires go together. There are some ways that you can determine that using a multimeter, but look it up if you're going to hook up a stepper motor for the first time. Now, controlling a stepper motor can be done a number of different ways. You have to keep in mind that stepper motors are not just on-off. You don't even really control their speed. All you do is you tell them when to step. And if you tell them to step really fast, well, then they'll spin faster. They still won't spin as fast typically as a continuous rotation motor because that's not what they're designed to do. But you do have to send them a continuously changing signal in order to get them to move. So you can do that with a dual H bridge, an L293D style chip, and you can control that manually from your Arduino and say, energize this coil, energize the next coil, flip the first coil around, energize it, flip the second coil around, energize it. You can send a series of pulses that will get your stepper motor moving. But you don't have to get all that fancy because, once again, somebody's come up with a stepper motor library, and you can define your stepper and say which pins it's hooked up to. And like I say, typically you'll be hooking up to just 4 pins. And then what it will do is all you need to do is you tell it mystepper.step, you tell it how many steps you would like it to go. So in this example program, they tell it to just take one step and keep track of it one step at a time. But you could tell it to take 100 steps, or if you wanted to spin in the opposite direction, you could say minus 100 steps and it would start spinning backwards. So there's a whole bunch of things you can do, but using the library is a step up from doing the manual coding. But even the library is going to put a lot of processing load onto your Arduino because it has to be processing that all the time. So what I tend to like to do is to invest in a few driver boards, and depending on the size of your stepper and your current demands, in other words, how much torque you need to get out of it, you can actually get some relatively inexpensive stepper motor control boards. And what's really nice about them is that they manage a whole bunch of different things for you, one of which is micro-stepping. And micro-stepping is where instead of turning one coil all the way on and the other coil all the way off to get your stepper to move, sometimes you want the motor to point in between the coils. So typically, if you just use the coils, you get about 180 to 200 steps per revolution. So that's good for most applications, but if you want more precision, you can go up to 8 times microstepping. In fact, there's 16 times microstepping, but the higher you go with your microstepping, the less confident you can be of your precision. But that would enable you to have, at 8 times microstepping, up to 1,600 different positions in one rotation of your output shaft. And that's pretty good, particularly if you're gearing that down as you hook it up into your drive mechanism for your CNC machine or your router, and that could turn into, you know, uh, thousands of steps per revolution. And depending on your thread pitch that you're using or your belt wheel diameter, belt pulley diameter that you're using to drive your mechanism, you could get very fine, precise control down to a thousandth of an inch or less. Anyways, the driver board really reduces your wiring and complexity because all you need to do is hook 2 pins up to your Arduino, one saying pin and one saying direction. And everything else on here you'll read in the manual, and it's got power and it's got ground and it's got places where you can put pins to control how much micro stepping you'd like. But all you need to do from your Arduino is you just need to have 2 lines, one for step and one for direction. And if the direction is high, your motor will turn in one direction. If the direction line is low, your motor will turn in the other direction. And in order to make your motor spin, you just send a continuous series of pulses down the line to the stepper motor driver, and the stepper motor driver knows the correct sequence to activate its output pins to drive the motor. Now, the other thing that these do that's really cool is represented by this little potentiometer right here. That is actually a tiny little potentiometer that gives some information to the chip right here. And what that lets you control is that lets you control the maximum current flowing through any of your pins at any one time. Now, obviously, the fact that this is a fairly small chip, you've got some fundamental controls on the maximum amount of current going through there, because otherwise you'll just start melting the copper off the board and toasting the chip. But this allows you to control that current very precisely and down below the tolerances of blowing up your board. And it's not so much that it's protecting your board, as what it's allowing you to do is it's allowing you to spin your motor faster. So typically, a stepper motor could be very happy being hooked up at 2, 3, 5 volts or something like that. And you could run that current through there all day long, and the resulting current, and it would never burn out because the natural resistance of each of the coils inside the stepper motor would limit the current at a low voltage. The catch is that each of those coils has inductance. And as I mentioned in a previous video, inductance is kind of like a freight train. Okay, picture your electricity as a freight train, and when it flows through that electricity flows through an inductor, it builds up momentum just like a freight train does. Now, that's a really poor model that's going to get me smacked around by some theoretical physicist because that's not what it does. What you're actually doing is you're building a magnetic field around the coil, and it takes time to establish the magnetic field, and it also takes time to shut the magnetic field down. And if you reverse the direction of the electric flow through the inductor, you now not only need to collapse that magnetic field, but you need to recreate a magnetic field flowing in the opposite direction. So in order to do that rapidly, you want to hit it with a very high voltage. Because you're hitting it with a high voltage, you can change that magnetic field strength more quickly. But because current in an inductor kind of behaves with that freight train-like momentum effect, you don't get that much current flow because you're still fighting against the existing magnetic field. So you can drive your steppers at very high voltages for very brief periods of time when you're trying to change the polarity of the coil and not have a problem with things going over current. The catch is that as soon as the stepper reaches its new and established position, well, now that freight train's up and running. It's moving along. You've established the magnetic field, and that magnetic field just wants to keep growing because you're hitting it with a high voltage signal. And all of a sudden, you're going to get too much current flowing through your stepper motor. It's going to heat up. Your chip's going to heat up. Your board's going to heat up, and you're going to start letting the magic smoke out. So what this does is this lets you set how much current you want to flow. And if your stepper motor can handle 1 amp on a coil, you can dial that in and you can monitor the current output and you can say, okay, I only want 1 amp of current flowing through this coil at any given time. And the chip will monitor that and it will engage its own pulse width modulation. Real like duty cycle pulse width modulation, not hobby servo PWM, but it will engage pulse width modulation to chop the amount of current that's going through there so that the average current going through there is back down to 1 amp or whatever you dial in at that pin. So anyway, some very neat features that you can get by using stepper motor driver boards, many of them relatively inexpensive. There are many choices and it's worth going online before you decide on the project that you're doing. You have to have some idea of what voltages and currents you're going to be working with and taking a look because the A4988 is a classic stepper motor driver chip, but there are some new ones out there that offer even more options and higher performance. If you're looking at bigger stepper motors, then you might want to move up to something like the DM542. And I've had students create stepper motor projects like 3D printer size things relatively inexpensively using A4988s. And the students who've gone up to build CNC machines, which are heavier duty because instead of just moving a lightweight little head, they have to be able to move, a cutting tool and the motor that drives the cutting tool, and they have to be able to push it through whatever material they're cutting. They are definitely going to need bigger motors with more current, and they've used bigger drivers. Therefore, you can get a driver like this for $24, something like this for $3 or $4. So it's actually not that expensive to quickly build a 3-axis CNC machine using stepper motors and a few drivers. Best of all, you can download a G-code interpreter for the Arduino. So if you've learned how to program a CNC machine using G-code, you can use all those exact same tools to run your own CNC machine. All right. Unfortunately, we can't simulate the stepper motor in TinkerCAD for you right now, but I hope that gives you an idea of what servos do, what steppers do, some of the differences between them, and why they're both awesome tools for what they do at precision motion control. Thank you very much. Have a great day.